Hi, this is Module 17 of Two-Dimensional Dynamics. Our learning outcome for today is to use the instantaneous center of zero velocity, which we discussed last module, to find the velocity of bodies in planar motion, two-dimensional motion. And so here was the information that we came up with last time for the IC. We said that if we can locate the IC, any point on a body is going to be equal to omega of that body crossed with a position vector from the IC to Q. And so let's go back and look at the crank arm piston cylinder problem that we looked at previously using the relative velocity equation. The IC method just gives us another tool for solving these equations. We go from knowns to unknowns. We know the angular velocity of body B1. We know that point O is a fixed point, so that's the IC for body B1. And so I can then write an equation using the IC. I can say that the velocity of A is equal to theta dot body B1 in the K direction crossed with R from the IC of body B1 to point A, or the velocity of A is equal to, again, theta dot B1 is 10 clockwise, which is going to be in the minus K direction. So I've got minus 10 K crossed with I go minus 3 in the I direction, plus 4 in the J direction. And I get the velocity of A then is equal to 40I plus 30J inches per second. Okay, so we keep going towards unknowns again. To go from A to B, I'm going to use the IC method, so I need to locate the IC for body B2, or the bar from A to B. We know that the velocity of A is up and to the right, 40I plus 30J. I can drop. We also know that the velocity of B then is going to have to be to the right because it's a slider mechanism or a piston, so this is VB. I can now drop perpendiculars from both of those velocity vectors, look where they intersect, and that will be my IC. So if I drop a perpendicular from this velocity vector and a perpendicular from this velocity vector, this is perpendicular, this is perpendicular. Where they cross will be the IC for body B2. And we know that this is on a 4-on-3 slope, okay, from our dimensions here. We also know that this distance is 12.4. Let's do this in a different color here. So this is 12.4 inches from B over to A. And I therefore know that this distance from O to B is 9.4 inches, because that's minus 3. And I want to locate the location of the I for body B2. I need to know this distance, or this height, which I'll call H. By similar triangles, I know that H is to 4 as 9.4 is to 3, and so H ends up being 12.53 inches, and that's the distance from here to here. So I've got the location of the IC for body B2. I can now use it to finish up the problem. So here again, here's the location of the IC. It's 12.53 inches below B for bar AB. I have already found the velocity of A. It's 40I plus 30J, or 50 inches per second total at this direction. So I've got the velocity of A by my instantaneous center equation is equal to theta dot B2, body B2 in the k direction, that's omega, crossed with r from the I for body B2 to point A. Okay? And when I do that, I get velocity of A was found to be 40I plus 30J. The angular velocity of bar B2 is unknown, so that's theta dot B2K, crossed with, in going from I to A, the position vector is minus 12.4 in the I direction and plus 16.53 in the J direction. So this is going to be minus 12.4 I plus 16.53 J. And I can now do my cross products, so I get 40I plus 30J equals, let's see, K cross I is minus J, so that, or excuse me, K cross I is plus J, but I have a minus 12.4 times theta dot B2, so that's going to be minus 12.4 theta dot B2 in the J direction, and then I've got K cross J is a minus I, 16.53 theta dot B2 in the I direction. Now I can match components, solve for the unknown, which is theta dot B2. I'll match I components. When I do that, I've got 40 equals minus 16.53 theta dot B2, or theta dot B2 equals minus 2.42, just as we found with the relative velocity equation. So we should get the same result. If we don't, we know we've done something wrong. It's interesting to note that if you match J components, you'll get the same result for theta dot B2, which you should. Finally, we found the velocity of A. We found the angular velocity of bar B2. Now, using that angular velocity in the IC, I can find the velocity for any point on bar AB. So the one I want to find is the velocity at the piston pin B. And so I'm going to write my relative velocity equation again, and I'll get the velocity of B is equal to theta dot B2 in the K direction crossed with a position vector from the IC for body B2 to point B. And we know that theta dot B2 is minus 2.42. We've solved for that. R from I of B2 to B is just 12.53 in the J direction. And if I do that cross products, I've got K cross J is minus I, but I've got a minus 2.42 times 12.53, so minus and minus is a plus. I get 30.3, and it's in the I direction, inches per second for the velocity of bar B. And so we get the same answer as we did using the relative velocity equation. Okay. That's solving a relative velocity, velocities on a planar rigid two-body or two-dimensional body. And I want to give you a chance to do it again using the IC method. So here's another worksheet for you, very similar, but it's great practice for you. And once you finish this, I have the solution in the module handouts, and I'll see you next time.